Hi, my name is Andy and I'm with Akai Corp. Today we're going to talk about VFDs and electric motors and what you need to know about them. Okay, so this is a setup that I put together so we can do some testing around eddy currents and capacitive coupling, or in general in terms of shaft voltages on motors. Pretty straightforward setup. We have a Durapulse AC drive, and this is a VFD, or a variable frequency drive. And then we have a motor attached to it through basically a quick coupling so that we can connect different motors. If you look over to my side here, we can run this big beast over with this same thing also. So let's talk about what a VFD does in terms of taking our 60 hertz power that's coming in, our 240, and converting it over to three-phase power at different frequencies. This little box here does a few things. The first thing it does is it takes this 60 hertz 240 volts and converts it over to a rectified wave. So we have a sine wave coming in and we convert it over to a rectified wave. From there, we now have a peak voltage, and we're going to filter that so we have a constant voltage. So we add filtering. So now we've gone from this sine wave to a rectified wave, and now to a fairly flat DC voltage. And that's where the magic actually happens after that. So inside this Durapulse and inside most VFDs, there are insulated gate bipolar transistors. That's a fancy name for an electronically controlled, very fast switch. And there's a microprocessor in here that knows how to control that switch. So now we have this high voltage DC rail that we can switch on and off onto three different lines. And in here, we have three lines. We have a ground and three phases. And each phase is built by the VFD to look like a sine wave, but it only has a high voltage rail to work with. So all it can do is turn something on or off, and that voltage goes right to the rail. It doesn't necessarily follow a sine wave. So how do you make a sine wave out of that? And what you do is you pulse, and the higher in the wave you need to be, the more you pulse. So for each one of these phases, this microprocessor and the IGBTs in here basically pulse at certain rates to be able to make it look like a sine wave. But it's not a sine wave. It's still a very fast rising and fast falling pulse that goes to a very high voltage rail. And that's a big difference than the sine wave that we fed into this box when we started. And the challenge with that is motors need to be able to handle those very fast rise times that we get out of the VFD. And this is where we start to see some problems. So when we actually provide three-phase power to this, there are pulses going through the windings that are very high frequency. And those high frequency pulses tend to create shaft voltages and currents that are built up onto the shaft. So if the motor is grounded, then because the shaft is insulated from the rest of the motor, it tends to build up voltages on the shaft that can lead to other problems. And the biggest problem that we get with that is that those shaft voltages transfer through the bearing into the case and slowly but surely destroy the bearing. This VFD creates thousands and thousands of high frequency spikes every minute, and the shaft voltages build up on the shaft and spark through the bearings thousands and thousands of times a second. So that slowly but surely destroys those bearings. So this setup that we have here is our test setup. We're able to control frequencies from half a hertz up to a few hundred hertz, pushing the motor way out of its tolerances, but still allowing us to demonstrate some of the challenges that we see with operating VFDs, even with inverter-duty motors.